Hello students, നമ്മൾ കഴിഞ്ഞ ക്ലാസ്സിൽ വെക്ടർ ഫീൽഡ്സിനെ എക്സാമ്പിൾസ് കണ്ടു. നമുക്ക് ഒരു ഇമ്പോർട്ടൻ്റ് എക്സാമ്പിൾ കൂടി ചെയ്യാം. സോ ഇറ്റ് ഈസ് കോൾഡ് ഗ്രേഡിയൻ ഫീൽഡ്. സോ gradient vector field. So suppose I have a function defined over a region in the space. So this is space, this is x-axis, y-axis, z-axis, and this is that region called G, and here I have a function, real valued function defined over this region, call it f. This is the real number system. Suppose that this is smooth. What is the meaning of smooth? All the partial derivatives of f of all orders exist and continuous. Now associated to this function f, we define a vector field. It is denoted by del f. I think you have seen this. Del f at a point x, y, z in the domain G is defined to be dou f by dou x at the point x, y, z into vector I plus dou f by dou y at the point x, y, z times vector j plus dou f by dou z at the point x, y, z at the point into vector k. For example, if f of x, y, z is equal to if f of x, y, z is equal to x, y, z, x into y into z, that's what it means, then del f is equal to what is dou f by dou x? It is yz. It is yz into vector I plus what is dou f by dou y? It is zx. Zx into vector j plus what is dou f by dou z? It is xy. Xy into vector k. And this vector field is very important. And del f stands for the derivative of f. Del f is actually it's called a gradient of f. Gradient of f, and it is actually the derivative of f. Now if I have a function defined over a region in the xy plane, then the corresponding definition of del f is dou f by dou x times vector I plus dou f by dou y vector j. Only two components will be there. So this is the definition of del f for a function defined over a region R in the xy plane, and f is from this R to the real number system. Okay, now we will go to work done. Suppose I have work done by a force. Suppose I have xy plane or xyz space, whatever it is, and so this is plane I am drawing, and here I have a region R, and in this region I have a force acting at every point x comma y in R. So force is a vector valued function. Force is a vector. So at this point, suppose the force is given by this vector f of x comma y, some function of x and y. At this point, let us say force is like this, f of x comma y, like that. This is the point x comma y now. So f at x comma y is like this. Now suppose I have a parameterized curve lying in R. So this is denoted by C. So C is parameterized as vector R of t equal to x of t vector I plus y of t vector j, where t varies in some interval a to b. So for each t here, I have R of t here. So this is what is meant by parameterized curve. And assume that R of t is smooth. That means derivatives of x and y with respect to t of all orders exist and continuous. Okay. Now the work done by the force F along this curve, that's what I am interested. So at this point, what is the force? If this point is x of t comma y of t, if this point on this curve C is x of t comma y of t, then what is the force at this point? It is given by f of x of t comma y of t. Okay. So suppose that it is like this at this point. At another point, suppose that it is like this. This is f of x of t comma y of t. At this point, x of t comma y of t, and so on. So at different points, force act in different magnitudes and in different directions. At this point, it is something like this, a very big magnitude. Then you know, work done is equal to force into displacement. But here the force is not uniform. So that simple formula, force into displacement, will not give you work, because at every point the force is different. So force into displacement means it is not exactly into, it is actually dot product, because in R you can give work done is equal to force into displacement, but in R2 it is force dot product with displacement vector. That's what. So the work done in this case by a variable force, that is obtained by integrating work done by F, the force F, along C is given by, so integral a to b or given by, let us first write the formula, given by integral over C force dot product with the infinitesimal displacement at that point. Now you sum over that or you integrate over that. So this is the work done. But how do you express this? You can express this by parameterizing f dot dr. So this is equal to integral a to b f of x of t comma y of t. Here it means f of x comma y. So if it is over c, then it is x of t comma y of t. Dot product with what is dr? Dr is, or dr by dt. Dr by dt is dx by dt vector I plus dy by dt vector j. So dr can be written as dr by dt dt, like this. So this is how we evaluate. This is the definition for work done, and this is how we evaluate. Okay. But what is dr by dt? Let us look at the unit tangent vector. Vector t. Vector t is equal to, so if this is the point r of t, then unit tangent vector at this point is given by like this. I will use a different color. This is the unit tangent vector, vector t. So t is equal to dr by dt divided by modulus of dr by dt. Modulus means absolute value or the norm of the vector. This is also equal to dr by ds. That also we have seen in the last class. Where s is arc length. Where s is the arc length. Why dr by ds is again t? That is because of chain rule. Dr by ds is, how do you write it? Let me draw a figure again. This is the xy plane. This is the region R, and here is the parameterized curve C. Here is the interval a comma b. Here you have t. This is r of t. This point is r of t. Now it is s of t is equal to integral t naught to t. This is the arc length. Norm of dr by d tau. That means velocity. D tau. Therefore, ds by dt is by definition, or is by fundamental theorem of calculus, what you will get? ds by dt is the value of the integrand at the upper limit, namely dr by dt. ds by dt by fundamental theorem of calculus, it is dr by dt. So let us substitute here. Where is that? No, here. So this is what is this? This is precisely ds by dt. dr by dt, norm of that is precisely ds by dt. So t is equal to t is equal to dr by dt divided by norm of dr by dt. Here I have norm here. So it is ds by dt. dr by dt divided by ds by dt is precisely dr by ds. That's what we have observed in the previous slide. Yes, t is equal to dr by ds. T equal to dr by ds. Okay, so let us substitute for work. Therefore, work done by f is equal to integral a to b f dot dr. That is the definition. But dr is tds. So it is f dot ds or f ds, not dot. Control Z. Oh no, what is dr? This implies, yes, this implies dr is equal to tds. So f dot dr becomes f dot tds. That means work done by f is equal to the integral of the tangential component of f with respect to the arc length of the tangential component of f. F dot t means tangential component of f. Thank you.